Engineering in Electrical and Electronics Engineering from CSI Institute of Technology, Thovalai, Kanyakumari district. He completed his schooling at Cathedral Higher Secondary School, Palayamkottai, Tirunelveli district. His professional career spans both academia and industry. He has worked as a lecturer at St. Peter Engineering College of Chennai, SCS SVMB University, Ennathur, Kanjipuram, and M&M Jain Engineering College, Thuraipakkam, Chennai. In the industry, he has served as a scientist at CDAC Trivandrum from 2007 to 2022 and currently holds a position at CDAC Hyderabad since 2022. Over the years, he has handled over various projects related to digital logic code design using RTL VHDL, including the development of a programmable vector interrupt controller with AMBA AHB interface, UART and I2C controllers, memory controllers with AMBA AHB interface, PHY interface for PCI, and a digital decimator. Additionally, he has conducted training programs such as a short-term course on FPGA-based SoC design and a 6-month certificate course on PGD VLSI. His expertise in digital design and training has contributed significantly to the field of VLSI and embedded systems development. We are confident that his insights and knowledge will provide valuable learning opportunities for all participants. Now, I welcome him to take over the session. Please, sir.
Yes, madam. Good evening, all. Hello.
Good evening, sir.
Yes. Today, we are going to discuss about reconfigurable hardware for next generation communication. So, in this session, I will tell about what is reconfigurable hardware, what are the features of the reconfigurable hardware, and what are the various applications of reconfigurable hardware. Then, what is the architecture of this FPGA? So, these are the things we are going to discuss. First one is reconfigurable hardware. Then I will tell about what is FPGA and what is its architecture, what are the resources in the FPGA, what are the various applications of the FPGA design. Then it is additional features of the FPGA that is called partial reconfiguration. Then how the design happening in FPGA design, how the EDA tool supporting for this FPGA design. First one is we'll think about what is reconfigurable hardware. So it is nothing but reconfigure means you can configure multiple times in a FPGA according to which resource you want, and you can support for various applications. So normally we have a conventional hardwares like this, all our hardware supporting devices. They are not programmable or reconfigurable. So it is like one time ASIC, they are all having ASICs. It is for fixed applications. But in FPGA, we are going to program whatever logic you want to implement. So that is a basic difference between ASIC and FPGA. ASIC is nothing but application specific integrated circuits. It is made for specific applications. But in FPGA, it is like a building blocks. Now you want to build a building, you have resources like bricks, this and that. So FPGA having a lot of resources, logic resources to make your own logics. It supports. You can anytime, multiple time you can program. So these are the basic difference between ASIC and FPGA. It have FPGA have much flexibility. It is time to market because ASIC is have a lot of lengthy time design process. So it moreover, if you go for multiple or if you want many ICs or number of ICs more, then you go for ASICs. For minimum number of IC designs, first you have to go for prototyping. So FPGA is for basically for prototyping purpose and small application developments. So FPGA's time to market is easy, design flow also less complexity, but ASIC is more complexity design. But ASIC is high performance device, and the power consumption also compared to ASIC is based on your optimization techniques you are using. ASIC you will get more optimization. Then the use cases for FPGA mainly for prototyping purpose and research purpose. So we will see what is FPGA. Before that, what is reconfigurable hardware. So this is the difference between conventional hardware reconfigurable hardware. So conventional hardware is a physical component. Discrete components are an electronic system, but in reconfigurable hardware, we have flexible medium to implement hardware circuits. In a conventional hardware, it is non-configurable after fabrications, but in reconfigurable hardware, like FPGA, after fabrication, you can program both the hardware and software. That is the main difference between conventional hardware and reconfigurable hardware. Some of the examples I am giving, conventional hardware are CPU, RAM, hard disk, or some other peripherals. But FPGA and CPLD are mainly for reconfigurable devices. This is the main difference between conventional hardware and reconfigurable hardware. So what is reconfigurable hardware? A hardware structure whose logic elements and their interconnections can be configured or reconfigured to implement the intention function logic circuits, whatever you want to design. Like if you want to design processor or any applications you want to develop. So you can develop through this FPGA board. So this is the diagram I'm showing that this is the, if you want to develop any applications, you can, if you use the board, there are three ways to you can implement. Either you have a, nowadays APIs are supporting high level synthesis. That means if you have expert in C code, if you write C code, then the tool will convert to the netlist, VHDL netlist, Verlag netlist. So you can implement the FPGA. Or other ways, if you have knowledge about digital logics and hardware descriptive languages like Verilog, VHDL, then you can write your own program, whatever function you want to implement. Then the tool will synthesis and implement and generate bit file. This is the actual flow in the FPGA design flow. Just I am telling what is reconfigurable hardware here. These are examples of reconfigurable hardware, FPGA and CPLD. So they are classified into three ways based on the granularity of the building blocks. Building blocks means a lot of FPGAs having small logics, digital logics or IP cores or interconnectors. So based on the granularity means the minimum bit level, how you implement. That is based on the granularity building blocks. Then the reconfiguration scheme, whether you are static or dynamic. Then coupling. These are the main architecture of the reconfigurable hardware. These three main architecture of the reconfigurable hardware classifications. The first one is we are fine grain. What is mean fine grain? It's a bit level primitives. Like if we go FPGA architectures, you can see that what is LUT, lookup tables, and config logic blocks and flip flops. These are the fine grain devices, fine grain architecture. FPGA is having fine grain architecture because it can implement bit level logic also. It's a primitives. But coarse grain means like somewhat multiple bits. So you can implement LU. Example for coarse grain FPGA structure is CPLD. For fine grain structure is FPGA. Next, that hybrid. Suppose if you want to implement some specific functions, the people go for fine grain hybrid architecture. Both support FPGA features and CPLD features. CPLD means configurable, complex program logic device. FPGA field programmable gate array. These are the. Then what is configuration? Just we saw that based on the scheme, what is static configure? Reconfigured resources are configured at the start of the execution time and changed during the application. One time FPGA we already told you the programmable device. So if you once program, then first at the initial stage you are programming bit file, that is called, you cannot alter your logics. That is called static. So reconfigure resources, one time you program, once you configure, then you are executing your logics. So this is called static. Next, this is a dynamic reconfiguration scheme. So once you are configuring, at a time you can execute in your application in the FPGA. So reconfiguration and execution is proceed at the same time. It is called dynamic reconfiguration scheme. So that one is how we are coupling with coupling nothing but you are connecting the resources. That means either closer to your CPU or away from CPU. That kind of things you can make your rough reconfigurable architecture. So reconfigurable architecture we already told you there are three classifications based on this granularity. Either maybe fine grained or coarse grained.
Excuse me, sir. Sir,
Yes, sir.
sir. Yeah, mobile கொஞ்சம் தள்ளி வச்சிருங்க. ஏன்னா அந்த எக்கோ அடிக்குது. நீங்க லேப்டாப்ல தானே பண்றீங்க?
இல்ல பிசி தான் பேசிட்டு இருக்கேன்.
ஓகே, கொஞ்சம் மொபைலை தள்ளி வச்சுக்கோங்க. அந்த எக்கோ அடிக்குது.
இப்போ ஓகேவா?
ஓகே சார், சூப்பர் சார். தேங்க்யூ சார். சாரி ஃபார் தட்.
No problem. This is coupling. This means I already told you refined hardware means based on the granularity we are classifying fine grain, hybrid grain, or coarse grain. Next one is how we are reconfiguring, either static reconfiguration or dynamic reconfiguration. Next classification is coupling. So coupling means this is your CPU, this is the coprocessor. So how they are communicating with each other, so close to the CPU or away from the CPU. This is will affect your uh, latency, power, throughput based on your coupling schemes. This is called reconfigure. Reconfigure hardware means this is the functional unit. Whatever logic you want to implement, this is called reconfigure functional unit. Like IP cores. IP core in the sense each design vendors, they are having own IP cores. You can plug and unplug in your system design. That is called reconfigure functional unit. So coprocessor is nothing but a special purpose. It's a processor can't do some work like GPU, graphic processing, cryptographic algorithm, some specific tasks coprocessor will do. This attached process having their own memory and interface process. The standalone process nothing but similar to the CPU. So it like multiple CPU can connect to your system. So this is another coupling methodology for your reconfigured system design. Next, what are the features of reconfigured hardware? Because I already told you reconfigure means you can program many times. Runtime also you can program. That is why it has flexibility compared to ASICs and other conventional hardware devices. So it is customizable and reliable resources. Resources in the sense it have a lot of resources. If you choose some specific vendors, they have own IP cores like peripheral designs or CPU cores. Like example, Xilinx having some ARM core 2, ARM core 9, two cores are there. So these are the resources like they're providing resources. Then it is already told you multiple time programmables. APGs are multiple time programmables. Then runtime programables. At one program running at a time, you can download your another program. Program nothing but your bit file or your logics, the functional unit. Then rapid support for rapid prototyping supports. Already doing prototype means your specifications can be, if you go ASICs, it will take lengthy time to design process. Suppose some error or flaw in this design process. After manufacturing of ASICs, you have faced lot of cost. You are losing lots of money. So instead of that, if you go for prototyping, then you can verify your design is yes, my design is working functionally and meeting time. That purpose of is called prototyping. So you can support for rapid prototyping support. Then hardware you can run parallelly for similar processor in your PGA. That called hardware processing. So it is have low NRE cost. Then other features are time to market is easily get available. Then the action of the design is the parties of it. Low energy consumption. You can have accelerators in your design. Then low energy consumption, then parallel processing, flexibility, low implementation cost. These are the various features of reconfigured hardware. So if you have expertise in digital design, then you can, if you know some cultural languages, you can develop your own digital system. Any logic you can design. So similarly, you can use. Suppose I'm not known about the hardware languages, but you want a system. You want to make a system. Then you can purchase IP cores. In the IP cores, you can test and make your own system. You plug and unplug the IP core, whatever you want with your processor. So that's another way of you can make your own system design. Then this is the on chip. You can program which part you want to program or which part you don't want. Like hardware, software, you can partition. It's the features of hardware. Hardware, software partitioning, on chip programming. Then it reduces the application runtime because the static programming, if you some logics you may or may not want, but even though we are programming, so entire logics will be using that static time programming. But the reconfig hardware, it reduces the application time runtime because your bit file has to be reduced. So time multiplexed applications for reconfig configuration. So the bit file get reduced. So your runtime also get reduced if you use reconfig hardware. It support drivers communication protocol also. Like communication protocol means if you interface for I2C or SBI or peripheral devices, and then on-chip communication like AMBA for processor communications, that kind of support you can use for recon hardware. So these are the various applications for reconfigure hardware, like medical electronics. If we go for that, we people nowadays using it testing this, how much our pressure, this and that, your heat, temperature, this kind of medical electronics, all electronic devices like uh, scanning, CT scan, this kind of things is it sensors we are using. So sensors, once sensors runtime we want to configure, we go for reconfigure hardware. So like ABS industries, uh, consumer electronics, like consumer electronics and communication infrastructure for 5G and network communications, wireless communications. Then automation vehicle, nowadays everything is IoT based. So nowadays we are using IoT. Autonomous vehicle also everything is sensor based only. So the semiconductor sensors are giving signal to this our board. We can process the signals in your FPGA reconfigure hardware. Then you can control all logics. So this kind of things we can do in auto reconfigure hardware. These are various applications: IoT, industrial automation, so smart cities, smart building, that called intelligence building. Because nowadays, like smart city, nowadays buildings are to secured purpose. We are going for this kind of intelligence
எக்ஸ்கியூஸ் மீ
buildings.
சார்,
Yes, sir.
கொஞ்சம் ஸ்லோவா, கொஞ்சம் ரொம்ப ஃபாஸ்டா போற மாதிரி இருக்கு.
Oh, okay, okay.
ஸ்லோவா ப்ளீஸ், கொஞ்சம்.
Okay, okay.
எஸ்.
These are applications, sir. Various applications for reconfigure hardware. Next, so again, nowadays we are seeing AI-based machine learning, because machine learning algorithm based is also nowadays available. So these various applications for these are reconfigure hardware, encryption engine, decryption engines, scalable computing, reconfigure computing, high performance computing, then this pattern recognition. So these are the areas we can use for reconfigure hardware. Now we go for what is FPGA. So this I already told you, FPGA is one of the reconfigure hardware. So this here we will see what is the architecture of FPGA. Before you going to design any logics, if you know architecture, then it is you can use whichever resource you want, you don't want. Like that, you can uh, choose the resources. So that's why we are going first FPGA resources, architecture. Architecture contains what is FPGA architectures and what are resources in the FPGA and what is the design flow. So any logic you have a certain design flow. Then what are the advantages of FPGA? Then what are the various applications? First, we will see the architecture of FPGA. So before that, what is FPGA? I already told you, is a field programmable gate array, or free fabricated silicon devices that can be electrically programmed in the field to become almost any kind of digital circuits or systems. So these are, I told you, configuration through FPGA's various methods. So I already told you, if you are not enough to do any hardware description language, you can go for schematic designs, because schematics IP cores are available. You can pick and plug and you make your system. Or somebody nowadays tools are supporting high level synthesis. So people are going for we are not enough to do HTLs, then they will directly go for C code, writing applications C code. Then the tool will support C to next level synthesis, netlist they will generate. Now, these are the various nowadays technologies growing. EDA tools are supporting these kind of things. This is the FPGA architectures. Normally, FPGA architecture is the basic FPGA architectures. It contains various logic blocks. Then it is, all are programmable logic blocks. That's why it's called field programmable. All are programmable. This IO also programmable. This connection also programmable. So logics also programmable. Then interconnect also programmable. So that's called, it's a field programmable gate array. So it contains an array of logic resources. This is the basic structure of the FPGA, architecture of the FPGA. Now we'll see the resources. So I already told you logic blocks. Logic blocks means it can be used to implement any combinational or sequential logics. If people know digital electronics, you know combinational, what is half adder or full adder or multiplexer, these kind of things, or sequential, any state machines or any logic is designed, flip flop like that. So interconnect is a wires and switches to connect input and output logic blocks. That is called interconnect. Just now it's shown you, this is interconnect logics. Then this is IO blocks. So it's external to the FPGA. So IO blocks nothing but is connected to the external world. So special logic blocks to peripheral to the external connections. Similarly, many logic resources, similarly clocking resources. Suppose my design is working, uh, output coming some frequency, so my logic should be working some another frequency. Then you can go for clocking management systems. So this is called clock management tiles, phase lock loop, clock buffers. These are the clocking resources in the available in the FPGA. Then various memory resources like LED-based RAM or black RAM. So based on your application, you can choose which RAM you want. Then IP cores. I already told you various IP cores. IP cores nothing but it's standard IEEE 1165 standards you should follow. You can design your own IP core. Various vendors they are developing own IP, then selling in the market. If you want to make a system, you can purchase IP. You can make your own system. That is called IP cores. Now, all other than that, embedded resources. Nowadays, just I told you, Zen having processor that is hardcore, softcore. Softcore is microplace and Intel Nias. These are example of softcore. Hardcore is Zen 7000 FPGA. Then, in addition to this, some course blocks are there. Debugging blocks. Once I implemented the logics, runtime you can debug whether my system signals are going properly, getting signals input output correct or not. And that kind of things you can verify through VIO, virtual input output, and integrated logic analyzer. These are the selling supporting debugging IPs. So additional IP of this selling architecture. These are the various FPGA resources. Then what we see detail what is configuration block. It is a basic component of an FPGA that provides the basic logic and storage functionality of the target application design. It comprises single basic logic elements or cluster of locally interconnected logic elements. It's like terminologies. A PLC consists of lookup table, that means function generator, and a flip flop. Some people they're using different terminology. So like Xilinx, they're calling it as logic cells, but ultra FPGA vendors they're calling it as logic elements. For functionality is same. The terminology they're using different names. Then another is fixed function logic blocks. So they have DSP slices, just as memory resources, block RAMs. Then advanced components. I already told you hardware macros and soft macros. Like hard macros are Zinc 7000 and soft micro plus. This is the building block of the FPGA. It's a basic building block of the FPGA. So like Xilinx, they're calling config logic blocks. So it contains lookup tables and flip-flop and mux. This is my input. So this is called 4-input lookup table. So if you want any 4-input logics, combination logics, then you can use this. The tool will use this lookup table, this config logic block. So 2x4 have a clock and this. If you want to take output, you have mux also there. So if you want clocked output, you can go for flip-flop. So we'll detail the. So config logic blocks is a primary resource of our design. It can use for both combination design and it have flip-flop. Each configurable logic blocks contain 2 slices. Slices means again some logics. So each slice contains LUT and flip-flop. The types of slices, we have 2 types of slices in Xilinx FPGA. One is for slice M and slice L. It's for memory usage purpose. So logic and arithmetic only for this. The tool will use this slice. For other purpose, this used by this slice M. It contains LUT also. So what is LUT? I already told you lookup table. To implement any combinational logics, just now I shown you 4-input lookup table. This one is a 4-input lookup table. What is a lookup table? This one. To implement logic functions or truth table for the input, it can use for combination or shift register, ROM, and anything you can implement. LUT contains memory cells. So because least element in a FPGA and multiplexers to implement the logic functions. Each cell it have a LUT and memory cells. So each memory cells having ones and zeros. And LUT with k inputs, it contains 2 per configuration bits. It can implement any k input Boolean functions. Just now shown you 4-input lookup table, so you can make 2x4 16 kind of Boolean functions you can use k input. then one value among these RAM bits will be available at LUT output depending on the value of fed on the line. Multiplexers, so Sony multiplexers and these multiplexers and LUT flip-flop. This is example for suppose your input variable is 4, then it called as input of LUT. So this is the 1, 2, 3, 4 input variable. Is LUT 4 input. Suppose your input variable is greater than the number of LUT. Number of LUT means the designer, the FPGA vendor having the FPGA having this input, 4 input LUT or 5 input LUT. They are the architecture of the FPGAs. It's vary from vendor to vendor. So if you are having your design having input variables greater than the input of the LUT, the present in the FPGA, then it will be configured like this. It will take 2 LUTs. So here is this is the number of input variables 4, it will take single LUT. But here if your input variable is more than that of the LUT present in the FPGA, then it will accommodate 2 LUTs for implement your function of the 4 input lookup variables. Then this is example for 4 input table. So it is having, I already told you 4 inputs is have 2 per 4 16 RAM cells are there. You can store ones and zeros. So you can implement any 4 input lookup table functions, sum of product or whatever logic you want to implement. If you want, you can take a clocked output because we have flip-flop, so you can take it output to the clocked output. So you can implement flip-flop also to implement the 1-bit register with EZ functionality. All flip-flops are D-type. The FPGA have D-type flip-flop. All flip-flops having a single clock input, active high chip enable, and an active SR input, set reset input. Then so various FPGA vendors, they are using different names. So just I told you the Versatile, it's Atal company now Microsemi, they are calling Versatile. Atal now called Microsemi. Then Adaptive Logic Management, Ultra now Intel taken over, and Ultra they are having adaptive logic models. Their FPGAs are statics and cyclone FPGAs. These are Xilinx, they're calling config logic slices. They are calling different names. So Xilinx, Vertex, Pattern, these are the FPGA of the particular companies. So the name is different, like Versatile, Slice, Adaptive, but all are doing the same kind of functionalities. Then this is routing. So what interconnections? So I already told you the FPGAs, everything's programmable. So interconnection also can be programmable. So programmable routing network provides routing connection among all logic blocks and IO blocks to implement any user-defined circuits. It consists of wires and programmable switches. So programmable switches are also configured using the programmable technology. So programmable technology means the FPGA designer normally we'll see what is program technologies. Actually, this is 3 types of FPGAs available in the market. SRAM based FPGA, anti-fused FPGA. Actually, they are making anti-fused FPGA. SRAM means it's a volatile memory based FPGA. Then flash program FPGA. These are non-volatiles. This is one-time programmable. Anti-fused is one-time program FPGA. So that then general purpose resource, connecting resources, the signals between CLBs and IOs. It's arranged in a horizontal vertical lines and direct interconnects, ones which connect logic blocks into the 4 surrounding connections. It's called direct interconnects. Then long line. They have high fan out to the signals should reach lengthy signals. So it needs high long line. It should have high fan out. Then clock lines, clock signal providers which runs all over the chips. So these are the interconnecting resources. Present the FPGA. So these are examples. So these are how the interconnectors are made in FPGA architecture. The info block, config logic blocks, the horizontal routing signal channels, then vertical routing channels, switch box, connection box. These are all routing resources, programmable routing resources. Then what is connection box? It is input. Just now shown you what is connection box. Some explanations. It's input output logic block to interconnect channels. That is called connection box. Then switch box. It's a horizontal channels to vertical channels. Transmission gate or pass sensors. Then routing resources, wires and switches that are used to transport signals in FPGA chip. IO logic, logic to logic, and input output logic. Then routing channels, then wire segments, what is a track, what is the capacity of routing channel. So these are various routing resources. Then IO resources. So initially I show you that programmable resource, logic resources, that is LUT, CLBs, or card macro, soft macro. Then we saw that interconnecting resources. Now seeing the IO resources. That means the APJ to external world. How we can program the external world of the APJ resources. So IO is input out block, special logic blocks at periphery of the device. It contains programmable input and output buffers, flip-flop, pull-up, pull-down resource registers, delay array, and bus keeper circuits. So suppose a vendor, another, you are using some other IC, they are having different IO, then we have to program according to that IC. So like that you can program your IO resources. So it is used to interface the FPGA logic to the external components. These are some types of two types are the user configure, then dedicated for configuration. But suppose that's why today we are configuring FPGA through bit streams. That pins are dedicated pins, like clock pins and configuration pins are dedicated pins. Some other pins are user configurable. This is example of Silence 7 series FPGA IO. So nowadays, so sky range means the voltage varying from 1.2 to 3.3 voltage operations, high performance. It's very, you can choose various pins, IO pins, based on the IO standards. It's a single standard or different standard. Difference means LVDS, LVCMOS, that kind of things. Then configuration bank voltage. See number of pins in a single bank. They will mention the APJ manufacturer. They will these banks comes to these pins comes to this bank 0, bank 1, like that they're making. Then it's easy interfacing to the standard memories. IO banks, dedicated pins for memory interface. So what is the buffer? Then what is the flip-flop? What is pull-up, pull-down resistors are used to assert the TSR pin, would otherwise be left floating for impedance mismatching, these kind of things, terminal. Then bus hold keeper. I told you IOs grouped into banks, number of IO blocks in a single bank. If you once you know the architecture, then you can identify which banks my pin is available. So I told you IO standards. It provides a specification to other vendors who create product designed to interface with the applications. So each standard often has its own specification for current or voltage or IO buffering and termination techniques. Termination techniques I already told you that pull-up resistor, pull-down resistor for impedance mismatching, a differential voltage signaling, that kind of things we are using termination techniques. Then voltage requirements for the IO signalings are dependent on the semiconductor process, that is the processing technologies. So it is my design work, this much voltage. It's a design, it's based on the FPGA designers. That means ASIC designers. FPGA is nothing but ASIC. It's a programmable ASICs. So it's designed by semiconductor processing methodologies. So these examples are very IO interfaces. This low voltage transient logic, low voltage CMOS logics, low voltage differentiation, high range applications like PC Express, Ethernet. So dedicated IOs are there. So this is an example of Silence FPGA architectures. I already told you. So configure logic blocks, then block RAMs, the IOs, clock management tails for clock management purpose, FIFO, first in logics, then buffer, then DSP slice, DSP logics, a multi-gigabit transceiver for high speed, high range, high speed applications like Ethernet, PC Express. That purpose of special IOs are there. This is called multi-gigabit transceivers. Transmitter receiver called transceivers. This is example for Silence Aicte 7 FPGA architecture. Now, just now we saw that what are the various resources available in the FPGA. Now, okay, resources available. How to build your system in your FPGA? That is called your FPGA design flow. We will see the step by step in our FPGA design flow. So this is, I already told you, if you have expertise in digital logics, or you have a, you know very well about this hardware languages, then you are writing your own code, HTL code, either maybe Verilog or VHDL. Then the tool, that is the ecosystem tools, Silence, ISC, Vivado, like Ultra Cyclones. With the FPGA vendor, their own tools they are producing. They have their own tool. Then only you can use that FPGA. That kind of tools will generate the binary file. Then you can implement in your FPGA. This is your FPGA architecture. You can program based on your HDL. You can program your own logic in your FPGA. The design flow symbol will. This is your design specification. A simple example, I can say that if you have some specification, example, you want to design some counter or half adder, whatever logics, any sequence logic or state machine, that may be your specification, design specification. If you think high level, if you have designed some system, then that is your design specification or your idea. These are three methods you can design your system in an FPGA. These are design inputs to the FPGA. I told you that HDL, yes, either you can use your VHDL or Verilog or nowadays system Verilog also supporting, or you can use your schematic logics. You can draw your own logic. If you don't know HDL, you have to plug and play. The IP resources available in the market, the tools also providing. That processor also available. So you can make your own system through schematic. You no need to know about this HDL. Then IP, I told you IP cores. These are the three methods entry for this design flow. Either HDL or schematic or IP cores. It's a design entry. Once, suppose example, I design my own logics in HDL, assuming you have half adder or something, or then you have to test your functionality. You test your truth table with your behavior simulations. You can write your own test bench. Then the logic you designed in the HDL, it's called your DUT, design under test. Then test bench is nothing but you are testing your logics, whether my design is working functionally correct or not. Suppose assume I'm giving AND gate. My input high means my output should get high. That kind of testing purpose called functional testing. That is called behavior simulation. Nowadays, that specific, we were also having simulation tools, Ultra having simulation tools for specific purpose. Simulation, mental graphics having one modelism simulation. Many people here in that modelism you are using in laboratory. That for specific simulation purpose. Then synthesis. Synthesis also different vendors having different tools. Synopsys having synthesis, Cadence having synthesis tools. Then Xilinx their own synthesis tools. Synthesis is nothing but your HDL code converted into your netlist. That I will show some examples. Then again you will test your functionality. After code written, we are testing the functionality. Synthesis means it take model from the particular FPGAs, then test the functionality. Again, you are testing my design is working or not. Then this is the implementation process. These three steps are the implementation process: translate, map, and place and route. So what is translate, map, and will detail. So this implementation will take care by the tool. We are no need to bother about that. Once you return the HDL code, you have to test the functional simulations. Then you test your synthesis simulations. My design is working or not. Suppose if you are very much about constraints, then you can give for timing constraints. The tool, you can generate STF file, standard delay format file. You can annotate. That means after routing, once your logics are like your bricks are here, you are connecting all bricks through routings. So how much time taking for routings and all. Then each inherent delay of the logics. That kind of things is shown in the STF. Then you can annotate the STF in your logics. Then you can simulate. That is called timing simulation. STF annotation. That means after place and route, it will calculate all values. Then the simulation is called timing simulation. That time only you can assure that my design work with this much frequency. It will check the critical path, input delay, output delay, what false path, that kind of things in the timing simulation. This is different. Nowadays, timing tools are there, timing verification tools are there, different things are there. But we are the front-end designers. I am not deep about these things. So tool will take care of these kind of things. Our aim is to understand the specifications and make the blocks, then develop your own system, either HDL schematic. Rest of things tool will take care. After implementations, we'll generate the bit files. So this is called binary files. Then you can implement. I already told you that there is a specific pins for the FPGA configuration pins. So that kind of things, JTAG or other programming methods are there. You can download the bit file in your FPGA. then the design will work according to your logics. This is the basic design flow in the FPGA. Any FPGA, it is a device independent design flow. If you go ultra design, ultra, if you go quarter tool, or if you are using Xilinx, Vivado, or Xilinx IAC, like Atal Libero tools. So each vendors, they have own design tools, but the design flow is common to all tools. This is a design stage, step-by-step procedures. So this is a board level implementation. Next, we will see in detailed manner. So this is design specifications. Suppose this is your design specifications. I'm implementing the RISC-V processor, something, or some other microcontroller I'm going to design. This is your specifications. So you are writing the VHL code. The VHL code you are testing. This is your DUT. I already told you, right? You over there, you will write your test bench. Then you will check the functionality. And nowadays, design verification also different domain is there. Design verification in the sense, just people are using system lock languages and the verification methodology, EVM, OVM, some other methodologies. So industry there was specifically for domain. There's a specific domain for design and verification domain. That people check our logics, nook and corner of the logic, design logics. So the functional simulations. Once the functional simulation done, you are checking it's okay. Then you go for synthesis circuits. That means your logic converted into this. Your code is converted into this logics. That is called synthesis. Then you are testing again post synthesis simulations. Then this post simulation. Then I am implementing. So I told you after routing connections, everything over, you are testing for functional timing simulations. Then you are going for configurations. That means after configuring something on-chip testing also available. I already told you some after implementing the FPGA. I already told you that embedded debugging IPs are there, so that you can use like ICAP or debugging IPs, VIO, ILA. This kind of the FPGA vendors, they have own debugging IPs, so you can test. Or in system logic analyzers are available, on-chip logic analyzers. Through the way you can test your test and debug your design. What is design specification? This is a functional requirement. Or you are designing the architecture. What do you want to make your system? What are should be present in your system? Which are the softwares? Which are the hardwares in your system? These are called specifications. I'll do design entry. So this example, this is RTL VHL. I'm touching this. What is VHL? It have an entity, get A, B as input and Q as the output. So you're writing Q is my output, A and B. That means AND gate, A or B. This is OR gate. So this is a schematic. This is a HDL, example VHL code. So this is one of the design entry. I told you 3 entries, schematic, IP cores, and HDLs. Among the 3 is this VHL code. So this is a relevant schematic. Primitives and IP code design entry. So primitive means the basic elements present in the FPGA. So vendor specific. Example, IO buffers, registers, DRAM, DSP blocks. These are the primitives provided by the FPGA's vendors. And I already told you hard IP cores. It is complex hardware blocks. So it is because already fixed. You cannot change the IOs. The vendor specific fixed IO locations. Like example, phase lock loop, multi-gigabit transceivers, Ethernet MAC, CPU. These are the hard IP cores. Then soft IP cores that you can program, you can configure one way, one application, depending on one application. It is simplex, simple to implement, fully described software. It is a synthesizable HDL code, highest flexibility. Example I told you, NIAS, Ultra, and Microprocessor Xilinx. These are soft IP cores. 2 ways of adding primitives and IP cores in your design. Either you can instantiate or inference. Instantiation means you are purchasing an IP or somebody may designed. You can use that design in your system design. You plug into your system. That is called instantiation. Already component available. Then you are with that component, you are making your system. That is called instantiation. That is a model explicitly available. You can add to the system. Inference means you are writing the code. Just now shown you that this code can be inferenced to this logic. Similarly, VHDL code or HDL code, the tool will infer what he written to map to the particular logics. So this is called instantiation. Here, they have designed some logics. So you are using the logics. Only port mapping. Port mapping sense you are connecting input output of the particular logics. But inference sense, you are writing the code, the tool will infer what he wrote. That is called inference. Then simulation, already told you, it's a process which a model of a digital circuits created and to test the functional. So example simulators, modelism, cadencing, IS, ILinks, different level of simulation already told you, behavior simulation, functional simulation, timing simulations, what is the purpose of each level of simulations. So once if a behavior simulation good, you can't assure that my design will work function because which devices is chosen, whether synthesis is proper or not. After timing simulation only you can assure that my design will work into the particular FPGA properly. So that's why we have to test step-by-step simulations. So this is example for HDL simulation. Just I shown you this is a waveform. Semantic graphics tools we can simulate like this. After writing a test source code, you write a test bench, then simulate. Then design synthesis. I'll tell you what is synthesis. It's a process of converting HDL to a gate level netlist. It's a process performed by the synthesis tool that takes standard cell libraries, constraints, and RTL code to produce a gate level. The synthesis tool will have three inputs. One is your HDL code, another is your constraints, and which library you are choosing. These are three input to the synthesis tool. So which library based on the design work. Some libraries having good delay component specific for high range of optimized for timing, like that you can choose libraries. So we'll see what is synthesis. I already told you automated synthesis tools. Example showing linear spectrum. This is specific synthesis tool. So these are the inputs. Input to the synthesis tool. I already told you three inputs. One is technology library, like Icon semiconductor, universal semiconductor. These are the IC fabrications. This TMC and UMC. So you can choose the library and HDL code and your constraints. This is a design constraint. These are the three inputs. Either you can go for timing constraints or IO constraints. That kind of constraints you can give it to the synthesis tool. So these three input taken by the synthesis, it will generate a netlist according to your input, three inputs. The netlist will be a Verilog, EDIF, electronic data energy format, Silex network file format, SDF, Verilog. So these are the output of the synthesis tools. Solid this is actually exam synthesis. So I am implementing here MUX. So this selection, based on selection, you will output going. So this is example for MUX. How HDL code can synthesis, how it is taken, the IO input buffer, and which LUT buffer taken. I already told you, that's why we shown you that architecture. So according to your code, HDL code, the tool will choose available resource in the FPGA and connect, make the logic. So the I already told you steps in synthesis. It's a translate. First step is translate. That means it convert your RTL HDL code is to technology independent. That means a vendor, FPGA vendor or library vendors have different resources. So this translate means it convert to your code into a technology independent representations. Logic in the Boolean equation form. Then next step is optimization. Optimization, since you are using like some product or some, like normally when the digital design we are doing KMF for premium leak and we are finding that kind of things. Here tool will take care of this optimization. We are reducing the resource. We are optimizing the logics. So optimization. Then technology mapping. These are the synthesis steps. So technology independent Boolean logic equivalent or mapped to the technology dependent library available in the resource in the your input, which library you have chosen. Based on that, it will map. Already today, these are the steps in synthesis. So this is your HTL. Then it is converted into transit technology dependent translation. Then after optimization, it will go to technology dependent mapping. This is what targeted technologies, which PGR, which library you have chosen. That is called steps in synthesis. These are three steps, main steps in synthesis. What is translated combines all netlist and constraints into the large netlist. Also, this is Xilinx, it generate this format, native generic database. User defined constraints, already pin and timing constraints you have to give. UCF file, user prototype consent files. So for translate, you have to do, it will take care of this kind of thing, translation. Then mapping, already told you, technology dependent mappings. After optimization, go for technology dependent mappings. So group of logical symbols, you'll choose which ICLBs and IOs based on your code. Then you compare the resources specified in the input netlist, native generic data, against the available resources in the target FPGA. If it is the resources insufficient or incorrectly specified resources, then it will generate the error while mapping. Then you divide the netlist circuit into subblocks to fit into the FPGA logic blocks. So example I shown you, if you have, suppose you are writing some code, 6 input, but my LUT having 4 input. So it will make it subblocks. Like that, it will aggregate, arrange the logics. After mapping, you will get the output called native circuit description. This is the output file from the mapping. Then placing. Basically, the NCD, native circuit description file, subblocks into FPGA. So this is called placing. So after construction of logics, where you want to place in your FPGA, that is called placing. It's here, there, wherever you want. Then routing. After placing, you are connecting the logics one and other. Logic to output. Like that, you are connecting. So connecting components and extract timing reports. That is called RC timing extractions. You'll calculate RC values. Then constraints. This is to implement based on your constraints, the tool will optimize. That is called constraints. There are various constraints and implementation of the constraints in an instruction given by the FPGA implementation tools to direct the mapping, placement, and timing other guidelines to follow while processing an FPGA design. UCF called user constraint file. Xilinx their own constraints XCC and Synopsys design constraint file. This is in the constraint file only you are telling that you use this IO, you can use this much clock period, this kind of things, clocking constraints, IO constraints, you can give into these constraint files. So I already told you that constraints also one of the important input of the synthesis. HTL, constraints, and library. So these are the constraints. After constraints, everything done, the tool will generate in a programming file. Implementation. Once implementation over, then tool will generate program file. The programming file is to convert the final NCD file into the format of the FPGA. Understand? The FPGA is bit file. It's a binary file. The FPGA is understanding the bit file. So to program the FPGA. So binary file can be directly loaded to the FPGA through JTAG interface or flash programming, other method of programming methodologies. So each FPGA has its own bitstream file format. For example, Xilinx they are calling the bit, generating program bit file is .bit. But Ultra they are calling SRAM object file SOF because SRAM is a volatile object FPGA, SRAM based FPGA. Their file name is called SOF, SRAM based object file. For Xilinx they are calling bit file. It's a binary file. So already today FPGA programming technologies, there are 3 types of FPGA programming technologies. SRAM based FPGA. This is a volatile one. Once the program again, once the power gone, then again you got to reprogram. That is called SRAM based FPGA. Then it's a flash program. It's a non-volatile one. Then antivirus is one-time programmable. These are three FPGA program technologies used. So mostly these are SRAM based FPGA mostly used because multiple time you can program. So this is a comparison of SRAM based FPGA and antivirus flash based FPGA technology, availability to program, how many times you can program, let's say volatile or not, whether we need external configuration file or not, good for prototyping, then IP security. These are the various compare between SRAM. You can choose which FPGA you want based on your application requirement. Then FPGA configurations. So once the program ready, you can configure FPGA. That is downloading your bit file to the FPGA. That is called FPGA configuration. It is a process of loading application specific configuration data into the FPGA through configuration interface pins. So this is your FPGA. This is configuration control logics. So configuration memory having store the configuration resources, so bit files. This control logic to download based on the control, you can program the FPGA. This is FPGA configuration. These are FPGA configuration mode. They are calling slave mode because this is your FPGA. This you have program some PROM. Once FPGA generating clock, then the FPGA called master programming. But the processor sending the clock to the FPGA, then this is called slave mode of programming. This is FPGA master mode programming, is FPGA slave mode of configurations. This is example JTAG mode. JTAG mode also is slave mode because this JTAG only generating the clock to the FPGA. JTAG is serial. Then next is programming methods. I already told you just how the bit streams are loaded to the FPGA. Either you can use JTAG or flash memory or configuration data can be stored in the onboard flash. So if you use this SRAM based FPGA JTAG, once power gone, the logic will not be available in the board. But flash mode it will available because it's a non-volatile memory based programming. Then another program methods you can remote program also is possible in the FPGA. So I am sitting here, you can through Ethernet you can program in FPGA. Remote programming supporting your FPGA. So various programming methods. And I already shown you what is the reconfigure hardware support. All nothing but FPGA's advantages. It's for parallel processing, rapid prototyping, flexibility, then cost efficiency, scalability. These are the advantages of FPGA. Then now this is our additional feature. This is the latest features in FPGA. That is called partial reconfiguration. Just we saw the things of static programming or one-time programming. One-time means once you program, you cannot alter the logic in the FPGA. But partial reconfiguration sense, at runtime you can change your function running in your FPGA. You can implement another logics like function 1 already running. At a time you can implement function 2 also. That's called partial reconfiguration. We'll see what is laboratory manner. It is a design feature of FPGA which allows a limited predefined portion. That is, we can call it a reconfigurable region of the FPGA to be configured by loading a partial configuration file. That is called partial. So user can define which region you want to become a partial reconfiguration region or dynamic region. So assume this is a FPGA. So this portion is called static. So this is called reconfigurable region. So this region you can implement. See here A1, A2, A3, A4. So these are time multiplex modules. I can run A1. After some time I can download bit to A2 or A3. So this is called reconfigurable region. This is additional feature of the FPGA. So region can be configured at runtime. So another logic is do not disturb the logics running on this place. So it is not disturbing the other logic running in FPGA. So parallelly run another logics in the configured regions. So that is called partial reconfiguration, additional features. This is the main importance for your reconfigurable. Nowadays you are like your weather monitoring or others. Currently system runtime system real-time applications, you want to immediately process the data, you can go for this kind of reconfigured hardware. Defense applications or weather monitoring, and medical applications. That's why we are telling the reconfigured hardware. So you can runtime program. That's why called partial reconfiguration. So these are terminology you must know before going for partial reconfiguration. What is reconfigurable logics, and then what is reconfigurable module, what is configuration memory, dynamic partial reconfiguration, what is frames, partition. Partition means you are splitting places, this place, or this module should be in my configuration region, or this module should be in a static region, like that you are partitioning. Then generating partial bit stream, what is the partition pin, static logics, then bus macro. These are the terminologies used in your partial reconfiguration design flow. So already today this is static logics. This is your reconfigurable partition. It have multiple bit file, partition bit file. So now we see the terminologies. What is frame? It represents the smallest reconfigured region with an FPGA. So each vendor they can tell the different way frames. They tell this much LUTs must be present within my frame, like that. They can declare. The vendor specific, they will tell. Then partition is a logic section of the design defined by the hierarchical boundary to be considered design reuse. So partition means you know which model again going to reuse. That kind of you are splitting your system into this model, my CPU or this some other peripherals. At what time I want to run, at one time I don't want to run a particular time. That kind of the designer has to decide which partitioning. Then reconfigure logic is any logic element that is part of the reconfigurable module. So these are the reconfigurable module, 4 modules. So this logic is any logic element that is a part of the reconfigurable module. These logic elements are modified when a partial bit file is loaded. So many types of logical components may be reconfigured, such as LUTs, flip-flop, and VRAM and DSP blocks. Then another, what is reconfigured module? It's a netlist of actual description that is implemented. Like I told you, F1, F2, function logic 1, function logic 2. These are reconfigured modules. So this we have 4 modules, A1, A2, A3, for various purpose. Then what is static logics? Static logics not disturbed by these while running or downloading the other bit files. That is called static logics. Once you program, you no need to alter. You cannot alter the logics. That is called static logics. You need to run parallelly. So this is what top level logics. Then what is dynamic partial reconfiguration? This is dynamic in the sense on the fly. We already saw static and dynamic. So dynamic means on the fly. So it's a partition. A portion of the FPGA is running, another portion is not disturbed by the others. So reconfiguration is to configure again. Once first time you are configuring, example function implemented in the FPGA F1, but F1 not disturbed while running after configuring the other F2. That's called dynamic partial reconfiguration. That means program a portion on the chip while rest in operation, rest of the circuit is operated. So what is the importance of partial reconfiguration? Why we go for partial reconfiguration? It's a time multiplex. I already told you. So time 1 you can implement, or time 2 implement. The designer has to decide when you want to implement these logics. So this is the time multiplexed function of the FPGA. It reduces the chip count because of the you no need to cover multiple FPGAs. You can implement a single FPGAs, different logics. So it can save the chip count, save power, create more flexible system, so separate algorithm. It reduces the configuration because of your bit size reduced. So the reconfiguration time also get reduced. It's transparent. See, you can well know to the which application running at a time. So that's a transparent applications. Whether my function 1 running or function 2 running, you can identify. So it's transparent to the applications. So it enhances system security. These are the main feature of partial reconfigurations. Then Already to static, what is static? The device is not active during the reconfigure process. So assume this is a configuration. After configuration, I am executing function A and function B. But if you want to execute function C, you get again reconfigure. This is static reconfigurations. But the dynamic reconfigurations, you see, it permits to change the device just without disturbing the other executions. This is called dynamic reconfiguration. This is parallelly executing B and partial execution C. In the previous case, if you it will wait and configure function C. That is called static partial reconfiguration. Again, reprogram. But here, running time, partial reconfiguration, dynamic partial reconfiguration. The advantages of partial reconfigurations, it is use of effective logic density because time multiplies. At time 1, you can implement one F1, at time 2, F2, like that. You have larger application, small chips. Then it reduced configuration time because already told you reduce the configuration size, bit size file. Then reduce the device count. You no need to go for multiple FPGA boards. You can implement single FPGA board for multiple logics. Efficient power management, enhanced flexibility in the system designs, and access to time market. Then another advantage of FPGAs is optimized system, adaptive hardware algorithms, on-chip hardware sharing. So the resource can be shared in a single FPGA. Then increase resource utilization, that's the same. Then provide continuous hardware servicing, upgrade hardware locally or remotely. This is advantage of partial reconfigurations. So these are the various applications of partial reconfiguration. Normally, it's software defined ratio runtime applications, then signal processing applications like image processing, signal processing, then pattern recognitions. Because this is used for various DSP plugs are available. So some specific floating point, so specific functions can be implemented in FPGA. So it will accelerate your system design. Then that's why it's for hardware acceleration, hardware security, and networking protocol supports, dynamic instruction architectures for processor operations. Now we saw the partial configuration and the architecture partial configuration advantages and applications. Now, which are tools available in the market and how to use the tools? EDA tools available in the market. I will show simple examples in EDA tools. So this is development tools to given by the each FPGA vendors. I already told you for reconfigure hardware. So a simple example. This is I told you Sync 7000 FPGA board. Now we are using set board. Available set board. So this portion is called processing system. This is called yellow portion is called program logics. So this is your HTML code can be implemented in this yellow portion logics. This is the fixed process system, which processor you want to use. Already today IP core available, hardcore macros available. So you can configure which system you want based on your applications. And that portion is called processor. You can either remove or add. This is called sync process system. This is program logic systems. This have external I/O, multiplex I/O, how they are communicating with the external world. It have ARM2 core processor. If you choose FPGA, they will see the features of the FPGA, whatever you are choosing FPGAs. The vendor will provide. I am showing the example here, saying 7000 FPGA architecture. So it have UART, SPI, CAN protocols, GPIO, and USB, the multiplex I/O, memory controllers. These are things available. Core ARM Cortex, A9, 2 cores are available, dual core available here. It interface this interface the AXI protocols, AMBA AXI, the communication on-chip protocol. Then how? So if you know the architecture, then if you are developing a system, after how you can develop your application. This is a simple example design flow of each EDA tools. I will show you example Vivada tool flow. So this is your requirement or specifications. Then you go for this is a Vivada tool. Vivado for either you have HTL or IP cores. I already told you can use for you to make your own system. And then this is another Vivada supporting SDK. It's only for application development. So once your logic created and generated the bit file in this tool Vivado, You can export the tool to this bit file to the SDK tool. Then here you can write your own C application code, application C code. Once C code is no error, you can generate the ELX file, embedded linking file, executable linking file, ELF file. That ELF file you generate in this SDK tool. Once no error in the ELF file, your application also you can run on the FPGA. After programming, your application will run without any problem. So after ELF file, you have to implement the program in your FPGA, that is through SDK tool itself. Then you have to run your application. This is the way of any system you can develop. So if we well expert in this architecture of any system design, you'll make here itself your system, the block level system design, or if you want HDL code, any system you can, like I told you, partially configured portions or IP cores you want to use, you can make the system design, block level system design in the Vivada tool or HDL tool. Then if it's successfully you're generating bit file, then you can go for STK tool. It's a software development kit tool. Here you can, the tool will have a supporting packages, OS support, barefoot, everything. Here you can generate bin file also, that flash program methodology. There are training we are giving. So here after generating ELF file, you can implement. Once you can execute it in the board. So this is a simple flow. Just to show you in the detailed manner here what is happening. So Vivada, you are launching the Vivada tool. There you are creating block designs. If you don't know HDL, then you are using blocks. Then add to the HDL level. If you want to add, then you add constraints and then generate a bit stream. Then Vivada part is over. Then you are going for SDK tool. SDK tool, you are exporting the hardware which generated from the Vivada with bit file everything. Then you are creating port support package, application programming in this SDK. After application, you are written a C code. I told you can program the FPGA. Then after you can execute, I told you ELF file. The ELF file should not be get error. It should not have any error. If ELF error, then you cannot implement the application in your FPGA. You cannot see your output. So this is the method of our Vivado tool flow. Any system you can design. These are the major vendor FPGAs available in the market, like Xilinx. What are the major FPGAs? What are the tools they are providing to develop their system in their own FPGA? Like Altis, Acronics. These are AI based. It's basically AI based. You can choose which range you want, like your how many logics you are going to use, or high-end applications or mid-range application. Like that, you can design. You can choose the FPGAs based on your requirement. These are the various FPGAs available in the market. There are FPGA families. So now I've shown you Xilinx. We are using Z-board. Z-board, we have Zinc 7000 FPGA, Arctic FPGA architecture. So you can choose your architecture based on your requirement. So these are the key available in the markets. Which purpose they are doing, making FPGA specific. They are focusing particular areas. So micro semi, they are using for aerospace and defense medical applications. Like that, you can choose which applications you want, IoT based or medical applications, automotive industries. Then you can choose particular tools. They will provide. If you purchase a board, they will provide the tools. If you want, I will show. These are the resources. You can go some web resources to learn about VLSI resources and FPGA development boards, Synapses. See, Synapses and Xilinx, they are having university program. You can register. You can download the tool, install the tool. You can free resources available in there. They are having university programs to interact with academia industry. They're supporting tools and some lectures also they're giving, curriculum also they're framing, like that Synapses and Xilinx people are doing. If you register their particular website, you can contact them. You can make your own setup laboratory in the academies, colleges. So now I will tell you what we are CDAC doing. CDAC, I'm working CDAC. This is a very thematic area of the CDAC. High performance computing, strategic electronics, then heritage, multi-level computing, software technologies, cyber securities, quantum computing. These are main thematic areas of education training. So education training, we are providing some centers. We are having 12 centers in around India. So some centers having MTech program, PG diploma program, PG diploma courses. So this is a short-term program. I am providing this. I already told you PG-based assessment design. I already given this kind of trainings. So this is Silence 7 architecture. Will teach in the short-term training. RTL design, IP core, how to create your own IP core and integrate with your design. Then various program methodology, SD card, you can generate pin file, QSP file, JTAG programming, IL2D, debugging purpose. These are the trainings we are providing for short-term training PGA. With this set board, we add on the SDK tools for graduates. They should know digital electronics, basic things enough. These are outcome of this training. Then this is the CDAC doing various post diploma graduate program. So many people are doing. They are conducting common admission tests all over India. Then they are getting admission to various centers. Different centers having different PG diploma courses. You can go through CDAC website. You can avail the course. The students can avail the course. Industry-oriented courses. Their placement opportunities are providing. That's all. If you want, I will show some example. We got a tool. Hello. So this is an example. I will show you got a tool. If you want, I will show you some more. So if you want, I'll show you simple logic how we are making. I'm going to go make half-order small project. Now already I designed some logic. That's why so this is a project. I'm using some half-order. This example I'm showing simply. So this RTL project, or suppose you have IP core vendors, you can go for IP core resources. These are various input methodology for RTL source or post synthesis project. Already synthesis logic available, you can put into your APGA. Then IO planning project, then importer project. So these are various input up to this tool. Now I'm adding file half adder example. This is my half adder test source code. This is my half adder source code. I told you DUT. This is VHL. Then I'm adding my test bench. So here adding IP. No, I don't have any IP, so I'm going for next constraints. This is my half adder constraint. Already written. I'm choosing set board. This is the way of designing methodology. First, we are creating project. So I will show you simple animation. So after your loader is designed, this is your source code DUT. So without test bench, you can run like this. If you suppose you have a test bench, you can add a test bench to the simulation source. So I'm on test bench. So here I'm running bigger simulation, so you can see in the waveform. So these are design flow method. Next you will go for synthesis and simulation. So once you check the functionality, so here you can check. You can check like this whether we input output getting same or not based on the input. You can check your truth table like that. So this next is your elaborated design. This is if you see the elaborated schematic view, this is without I told you before before mapping technology independent. So you can see the schematic. What is my half adder? Oh, this is my half adder. I return the code here. So source code, this is my source code. Return the code half adder. A XOR B and A and B come carry. So this is my schematic of half adder. Then for synthesis, the tool will take care of all constraints. Only the constraints you have to which board you want to implement. That kind of constraints you have to give. That I have already written the code. Constraints code here. So now we'll see after synthesis running. And synthesis successfully. So open, you can see the open synthesis design. See, this is design is technology mapped. We can already choose a set board. So this is technology mapped synthesis at least. We took two LUTs. How many resources? It used 6 cells and how many IOs and use how many nets. This is one net. You can check how many nets are there. Some nets, 8 nets are there. Like that, you can check for optimization purpose later. You can run implementation. Before running implementation, you have to check your constraints are file or not, because before generating bit file we need to provide constraint files. Constraint means you are in the FPGA vendor, they will tell the board having this LUD or OLED or Ethernet. You have to connect this pin, that pin. They are giving the constraints, pin mapping. That is called constraints. So now implementing. Implementation done. So once implementation, you can view your schematic also implementation. See. So these are FPGA. So you can zoom, you can see which pins are connected, how many LUTs are there, how many slices are there. So this is based on our FPGA architecture, you can see that you can connect it. So vendor. So this is a slice. I already showed you the FPGA architecture. Any DSPs are there, any routing resources, special macros, codes. So these are the pins connected based on, you can see this N0 into IO, these IO pins. These are logic resources. So like that, for floor planning, you can do that. For partial configuration, you must do floor planning, partition and all. This kind of essential for the partial configuration. Once this, you can generate a bit stream. So sources, I only show you what is constraint. This is a constraint. This constraint is, so we are mapping which IO goes to go, which pin. This is a pin F2, 22. This is once you, the FPGA board manufacturer will give the guide, design guide. You can, based on that, you can configure which pin you want, which voltage level, early to do low voltage CMOS, the IO standards. Then generate bit stream. At present, I don't have a board. I simply am showing. That's all. This is the basic flow for VADO. Once you flow over, then we go for another tool SDK. At present, I think SDK is not license. It is license vanished. So this is the basic flow. This I am showing simple half adder. So here we generated bit stream successfully. So after that, if you connect the board and you can implement the your logic. This is a basic flow for simple example. Suppose we want a high level system, you can create your own block design. You can create another project like one block. See, check the IP course available in the this is IP course available. You can create block designs. And so you want a IPs available. So these are IPs. You can use various IPs based on your requirement. See, these are automated industrial applications, AXI, base IPs, DSP applications. Like that, you can choose your IPs. Suppose you can choose and connect. Suppose I'm base IP multiplayer. I told you debug IPs, image processing. These are various IPs they're providing. I told you we search here. Search also. Search VIO. You can get IPs like Zinc 7000 fund process. You can get the IPs. So this is in processing. You can configure which based on your requirement. If you want UART or not, peripheral IOs. So you can select whichever you want. Like that, you can generate your own system. If once you build the system, then you go for like procedure I told you how to implement a half adder. It will generate bit file. Then after generating bit file, you got to launch the SDK tools. But here it's not supporting. That's why I think the license SDK is not available. This is the basic flow. Then you can write the application name, SDK tools. That's all. So I am concluding here. If you have any doubt, you can ask. Sir? Huh?
Sir, thank you.
Any,
Sir.
any doubt they
Thank
can
you, sir.
ask.
Thank you for your valuable presentation. Definitely, your insight regarding the FPGA architecture, input and output standards, and the application-specific integrated circuits, ASIC designs, how it can be integrated in the semiconductor industries, and what are all the reason technologies available. All those things given a very big idea about the process. And also, you listed a few PG diploma courses which are all going to conduct by the CDOC. So definitely, it is the very useful session, sir. And
Yes,
also, the live simulation which you share is really useful. Actually, nowadays, simulation thing will give you a lot of insights how we are going to integrate the circuits, how we are going to testing the logics, implement the logics. For example, you share the source code of half adder, how it can be implemented with the help of a test bench, and how the signals from 0 to 1 and 1 to 0, all those things we clearly observed. On behalf of St. Joseph College of Engineering, the team of ECE extend a heartfelt thank for you. And also, we received a few queries in the chat box, sir. One of
okay,
the
sir.
query is, can you please list out the some freeware which is available in online resources for learning the VLSI course?
They can go for this Xilinx website. I told you already, Xilinx university programs. The last slide I shown some resources. You can go through website, no? Everything VLSI resources. You can go everything. You'll get what are free resources available.
Okay, sir. Okay, sir. Okay, sir.
Xilinx website, if you go, no, they can register. If you have a register URL, you can register your own email ID. Then they'll build the license tool. You can runtime and installation tool, free tool available. Xilinx providing free tools.
Okay, sir. Okay, sir. Dear participants, if you have any queries, you can unmute your mic and interact with our resource person. He is always ready to share knowledge and regarding your queries. Participants, you can unmute your mic and you can interact with our resource person. Dear participants, you can unmute your mic and interact with our resource person. Otherwise, you can post your queries in the chat box.
Otherwise, I can take a mail. My mail ID I will provide here. Chat.
Sir, please, can you post your mail ID, sir, or details?
Okay.
Any queries? We think there is no direct discussion. The participants, if you
Sir, so one person asking, tell me the course. Course
Yes,
means,
sir. Yes, sir.
sir, already told.
उडाला मला फुटला ते उडाला सकाळी मला वडे करून दिले नंतर कपडे धुतले पाण्यामध्ये हात माझी दोन चक्कर येऊन पडली तिला दवाखान्यात नेलं फुटलं ते अशीच गेली ती कोणाला लवकर का आता एक्झामचा टाइम असतो ना
Sir, Saravanan, sir.
Yes, sir. Yes, sir.
Sir, Mr. Saravanan, scientist D from VLSI DAC, Hyderabad, India. Actually, bearing your busy schedule, you accepted to be part of this 6 days Atal program. Your presentation was very awesome. And it was very enjoyable for all the circuit branch listeners. All the circuit branch listeners are needing these type of things to know the hardwares and the softwares, because for better work performance of software we need the perform better hardwares and high speed hardware and adaptable hardware and reconfigurable hardware. We have discussed much. The participants will have a further tie-up contact with you if whenever they need any help from you. Thank you very much, sir. Thank you once again, sir.
Thank you, sir. Thank you for all participants for patient listening.
Thank you, sir. Professor, Dr. Ganeshman, sir. Sir, Professor Dr. Ganeshman, sir.
Dear participants.
Yes, sir. Professor, sir.
Professor Chinnaya.
Yes, sir. Thank you, sir. Good evening. Good evening, sir.
Good evening.
Sir, just actually participants were in the meeting right from the 6 o'clock. Can we give a 5 minutes break, sir?
Definitely. Please.
Yes.
Please.
Thank you, sir. Exactly after 5 minutes, we will begin the meeting, sir. Thank you very much.